Let us revise about the valence bond theory in coordination compounds. Valence bond theory, and in short form we write VBT. So valence bond theory in coordination compounds. In coordination compounds. Now this valence bond theory was developed by Linus Pauling. And according to this theory, the bond between the metal and the ligand is covalent. And according to this theory, metal act as a Lewis acid and provides empty atomic orbitals, not singly filled, empty atomic orbitals equals to its coordination number. Equals to its coordination number. So if the coordination number is 4, then the metal has to provide 4 empty atomic orbitals, and if the coordination number is 6, then the metal has to provide 6 empty atomic orbitals. Now ligands are Lewis bases, donates electron pairs to the metal atoms, donates electron pair to the metal atom. Now the atomic orbitals used by the metal atom in accepting electron pairs from the ligand decides the hybridization. Suppose the metal is using 1s and 3p's, then the hybridization will be sp3. If the metal is using 1d, 1s and 3p's, then the hybridization will be dsp3, and so on. Now if any unpaired electron present then the complex will show paramagnetism and attracted towards the magnetic field. Show paramagnetism, and if the metal is using any d atomic orbital from the n-1 shell, then the complex is called inner orbital complex, otherwise outer orbital. Inner orbital complex, otherwise outer orbital. So we take now some examples to explain the valence bond theory. And the first example is this one. It's a chromium complex CrH2O6. Now look at the steps how we work out the valence bond theory in complexes. Now the step 1 is the oxidation state of chromium is 3+. So we should write the configuration of chromium 3+, argon 3D3. Then we draw the box diagram. Now this is a box diagram. And the chromium 3+ has 3 unpaired electrons in the 3D subshell. And the coordination number of chromium in this complex is 6. Of chromium is 6, and whenever the coordination number is 6, it means the geometry is octahedral. Now chromium has to provide 6 vacant atomic orbitals, but there are only 2 available. So chromium has to use the 4 atomic orbitals from the outer shell, that is the 4th shell. So chromium uses 1 from the 4s and 3 from the 4p. Now all these 6 empty atomic orbitals, they hybridize, they form hybrid orbitals. Then each hybrid orbital accept lone pair from the ligand. Now this cross indicates the lone pair donated by the ligand. Now since the hybridization involves the 2 d atomic orbitals from the 3d, 1 from the s and 3 p's, so the hybridization in this case d2 sp3, geometry is octahedral as the coordination number is 6. Now 3 unpaired electrons present. These are the 3 unpaired electrons present. As a result, the complex will show paramagnetism. So the complex is paramagnetic, and the chromium has used 2 orbitals from the inner shell. Now these are the 2 orbitals used from the n-1d subshell. That's why the complex is inner orbital complex. Inner orbital complex. Now these are the steps you have to follow whenever the complex is given, and you have to explain the geometry, hybridization, magnetic properties using valence bond theory. Now let us take one more example. Now this example is of Fe F6 and 3 negative. Now again iron oxidation state is 3 plus and its configuration is argon 3d5, and the 5 electrons in the d subshell are unpaired, no vacant orbital available. Now since the coordination number of iron is 6, iron has to provide 6 vacant atomic orbitals. So iron is using all 6 vacant atomic orbitals from the outer shell, 1 4s, 3 4p's and 2 from the 4d. Now all these they hybridize, they form hybrid orbitals, then they accept the lone pair from the ligand. Now in this case the hybridization is at sp3d2. Geometry is octahedral since the coordination number is 6, and you have 5 unpaired electrons present, so the complex will show paramagnetism attracted towards the magnetic field. It will show paramagnetism, and the complex is outer orbital complex, as all the orbitals used by iron are from the outermost 4th shell. Now another example is NiCl4 and 2 negative. Now in this case the nickel oxidation state is 2 plus and the configuration is argon 3d8. Now this is a box diagram for nickel 2 plus. There are 2 unpaired electrons present and there is no vacant atomic orbital available. So nickel has to use all orbitals from the outer shell, and since the coordination number of nickel is 4, nickel has to provide 4 empty atomic orbitals. So this 1s and 3p's they hybridize to form hybrid orbitals and then accept lone pair from the ligand. This cross indicates the lone pair donated by the ligand. So in this case the hybridization is sp3 and the geometry is tetrahedral. sp3 means tetrahedral and it is paramagnetic since we have 2 unpaired electrons present, and the complex is called outer orbital complex. Outer orbital complex. Now when the ligand is a CO, carbonyl, Cn minus, Or we have a didentate ligands like En. Example is En oxalator. Then the pairing of electrons takes place in the d subshell. Then the pairing of electrons takes place in the d subshell. Now, for example, we are given NiCN whole 4 and 2 negative. This is very important example. Now, nickel is in the +2 oxidation state with a configuration of argon 3d8. Now, since Cn is present, so the pairing of electron will take place. So, all these 8 electrons in the d subshell present as 4 pairs. So, one of the d atomic orbital is vacant, one of the d atomic orbital is empty. As a result, the nickel uses one atomic orbital from the 3d subshell, and the coordination number of nickel is 4, so it uses one from the 3d, one from the 4s, and two from the 4p. As a result, the hybridization in this case is dsp2, and the geometry is square planar. dsp2 means it is a square planar, and the complex is diamagnetic since there is no unpaired electron present, and it is inner orbital complex, as one of the atomic orbital used by nickel is from the 3d subshell. It is the inner orbital complex. But remember, up to d3 electronic configuration, there is no effect of the ligand on the configuration. There is no effect of ligand on the electronic configuration. So all chromium 3 plus complexes are octahedral, D2sp3 hybridization, paramagnetic with 3 unpaired electrons, with 3 unpaired electrons, irrespective of the ligand present. Irrespective of the ligand present. So no pairing of electron takes place in chromium 3 plus, whether it is a Cn minus, CO, or you have a amine or water, it doesn't matter. So all chromium 3 plus complexes have a configuration 3d3, hybridization D2sp3, paramagnetic with 3 unpaired electrons, inner orbital like this. So this is about the valence bond theory in coordination compounds.